Thanks for watching this explanation of AlphaGo Zero. AlphaGo Zero is different from AlphaGo because it uses less prior encoded knowledge, whether it's in the form of supervised learning from human expert moves or in the input state representation to the neural network. AlphaGo Zero also uses a single residual neural network for the policy and value network and uses a very interesting extension to the self-play training by emulating the Monte Carlo tree search. This video is in a series of going from AlphaGo to MuZero, inspired by the Kaggle Connect X competition. This video will explain the follow-up to AlphaGo, AlphaGo Zero. Whereas AlphaGo is seeded with supervised learning of human expert moves so that it can train its policy network to exactly mimic the human experts, and that is how they start off the training of AlphaGo. AlphaGo Zero starts from scratch with random weights and trains itself purely through self-play. The self-play in AlphaGo Zero is different from in AlphaGo because it uses the Monte Carlo tree search, which is a way of getting a better action by doing the simulation where you look ahead and see what the better actions would be. And AlphaGo Zero uses this to sort of imitate the Monte Carlo tree search. So the Monte Carlo tree search produces a better distribution over actions than the policy network originally has. And they use this mapping from the Monte Carlo tree search in order to train the policy network. Also interestingly in AlphaGo Zero is that they combine the policy network and the value network into one neural network. In this case, rather than just a simple convolutional neural network, they're using the residual network. It's got these skip connections and then the batch normalization. Also in this paper, they're using a input representation that just contains of the input, the board, rather than having these handcrafted features. So it's just the board state and then having the last 8 concatenated together so that it has a little bit of a sense of history, because alone the AlphaGo, the Go board, doesn't obey the Markov property where the state is all you need to predict the future. So you have to append some of the previous positions of the board in order to make it so the current state representation can predict the future. This list from their paper provides a quick overview of the changes from AlphaGo to AlphaGo Zero. The first is that it's trained solely by self-play reinforcement learning, whereas the AlphaGo algorithm is originally seeded by doing supervised learning with the policy network so that it maps the states to actions exactly the same as the expert moves in this KGS dataset. So for this reason, it's called tabula rasa, or blank slate, meaning that it's like a blank slate algorithm compared to being biased with some prior encoded knowledge. So then the next change is that it only uses black and white stones from the board as input features. So AlphaGo has this first 19 by 19 feature plane that is the board state, and then it has these 47 handcrafted feature planes, as well as the board. So it's using a lot of handcrafted features in the AlphaGo algorithm compared to AlphaGo Zero. The next change is that it's a single neural network. So there isn't a separate policy and value network. Rather, it's kind of like a multitask network. They share the same feature extraction base, then you have separate heads for policy and value network. So you have like a 3-layer policy network and like a 2-layer value network. So it shares the same feature extraction, and then it has separate heads that map states to actions, and then a separate head that predicts the winning probability from that state. The fourth is that it has a simpler tree search that relies upon the single neural net to evaluate positions and sample moves without performing any Monte Carlo rollouts. So in the previous AlphaGo, we had this lightweight rollout policy that we used to, when we got to a leaf node in our Monte Carlo tree search, we'd send that rollout policy all the way down to the end of the game, and then we'd get that Z sub L, whether we won or lost in the rollout policy, and use that to update the max values in the Monte Carlo tree search. So in this case, what we're doing instead is we're incorporating look-ahead search inside the training loop. So what's going to happen is we have the policy network and the value network are now the same neural network. So they're going to be used in the Monte Carlo tree search, and then the Monte Carlo tree search's distribution over actions is going to be used to update the policy network. So the Monte Carlo tree search is seen as a policy improvement algorithm that you stack on top of the policy network. It produces a better distribution over actions by doing that look-ahead search. So you're going to use that look-ahead search and the results of that to form this new data set that's going to be used to train the policy network, and the details of that we'll get into in the video. The input representation in AlphaGo Zero is a bit more impressive than AlphaGo because it doesn't use any of these handcrafted features. What it does is it has these 19 by 19 feature planes which represent the status of the board. So what you have here is you're concatenating the previous 8 states. So you have, say, this is the current board representation, and then say maybe this feature plane would be like the board position 4 moves ago. And so they explain that this is because you need this history in order to make legal moves in the way that the game Go works. The next interesting detail from AlphaGo Zero to compare to AlphaGo is that whereas AlphaGo used a simple convolutional neural network, AlphaGo Zero is going to use a residual neural network that's formulated in this way described in their paper. So using things like the skip connections, having the batch normalization layers, the ReLUs, and they use the same shared feature extractor, and then they're separated out into these two separate heads. So the policy head has this architecture where it's mapping the state to the action, and the value head has this architecture where it's mapping it into the scalar, the probability of the prediction of the reward given the current state. So this trend, this AlphaGo Zero starts this trend that's now continued in things like the hide and seek agent from OpenAI and Dota 2 and all this stuff, where they're using these much more complex neural networks to map state to actions and do value prediction in these kind of game playing AIs. This plot shows an ablation that assigns a contribution of architecture, comparing the new residual neural network used for playing Go compared to the convolutional neural network from AlphaGo. The purple chart shows the dual Resonant. So dual versus separate in these plots means that you have one neural network that does policy and value estimation compared to separate having a separate policy network and a separate value network. So you see in the ELO rating metric, which is kind of like their version of accuracy, it's like the metric of higher is better and it's the ultimate metric. The purple score, the dual Resonant sharing both tasks performs the best, and you have a similar performance when you have the separate policy and value network but both sharing the residual architecture compared to the convolutional network that is doing both policy and value estimation. It's kind of interesting to think that maybe like the multitask of doing policy and value in the same shared feature extractor is improving upon the ability to do this. Then in the blue, you have the separate convolutional network, the way that AlphaGo is constructed. So comparing the light blue where you have separate policy, separate value, compared to AlphaGo Zero, which is the purple having the policy and the value network together in this Resonant architecture. These other two plots are something that we'll see again in the presentation. It's using this network to go back to that KGS human expert data set and predict things like the moves that they're going to make in a given state. So you see that in this case, they're about the same with respect to predicting what move the expert is going to make given a state. And then you see that actually the AlphaGo algorithm, or actually, sorry, this is a mean squared error plot. So it is better at predicting the value of the state in the human game data set. The core idea of AlphaGo Zero is that it's going to use Monte Carlo tree search as a policy improvement algorithm in order to construct the data to improve upon the policy in the self-play training loop. So the Monte Carlo tree search is kind of this heuristic tree search that's used on top of making decisions with a policy network and a value network. So what you do is you start off with an initial state and then you assign these weights to each edges. So these edges represent potential moves that you could take from a given position. So say it's like place a black tile here or place a black tile here from this starting state. So you have this Q plus U, and if you want the details of that, you can check out a video I made on AlphaGo, or you could read the AlphaGo paper as well as AlphaGo Zero. Both describe how they do this. Basically, it's the value network estimate plus some weighting of the probability distribution of the actions assigned by the policy network, and it's weighted by how many times you visit the node so that you visit it less often and encourage exploration. So you also have some kind of like an epsilon greedy where you don't always take the max. Sometimes with probability epsilon, you take the max decision, and then 1 minus epsilon, you choose randomly amongst the edges instead. But what you would do is you traverse down this tree and you reach a leaf node where you then use the policy network to construct a new node, and then you would back up the data from the new node to the Monte Carlo search tree, and you would iterate on this. So the Monte Carlo tree search uses this look ahead to get a better sense of the action to take at the next step. By looking all the way to say 8 levels deep, you get a better sense of the move to take right now. And that idea is key to how you train AlphaGo Zero. By using the data found by these Monte Carlo simulations, you try to put this directly into the original policy so that it can clone the results of running a Monte Carlo tree search from a given state. So the idea is that as we're doing self-play, we're running Monte Carlo tree search simulations from each state by running 1.6 thousand simulations, meaning 1.6 thousand times that the Monte Carlo tree search goes and tries to find a new leaf node to expand. And then we use this to train our original policy network. So the way that we do this is we take the distribution over actions that the Monte Carlo tree search decides upon, and we use this as learning data for our loss on our policy/value network. So this is the loss function that's used to update the neural network. So what we have is the P and the V come out from our neural network, from the original state. The V being the value estimate, the guess of what reward we're going to receive from the state, and the P is our distribution over actions, what moves we want to make from that state. So the way we're going to update this is we're going to multiply the pi transpose times log P. This denotes the Monte Carlo distribution is this pi, and the P is the distribution from the neural network. So basically we're penalizing it from being much different from the Monte Carlo search's distribution over actions. And then we're subtracting the Z minus V, Z being the actual return that was experienced in this episode, and V being the prediction from the neural network. So we combine both of these terms in the same loss function, and then you add this C of the L2 norm of the weights, which is kind of like a weight regularization term, but these two are the heart of the algorithm. In the paper, the authors first report the results of training a 20-layer residual neural network for 3 days. In this 3 days of training, they get 4.9 million games of self-play, which each move in the self-play loop having 1.6 thousand simulations for the Monte Carlo tree search, amounting to about half a second of thinking time per move. Thinking time describing this simulation in the Monte Carlo tree search. So then the parameters of the neural network, this 20-layer residual network with the 2 separate heads, are updated from the 700,000 mini batches. These pairs of state, the policy produced by the Monte Carlo tree search, and then the result that ended up happening in that full game sequence. So then you have the AlphaGo Zero outperforms the AlphaGo Lee from the original paper after these 3 days of training, or 36 hours, there's about 1.5 days, and that AlphaGo Lee algorithm had been trained over several months. So then after 72 hours of training, which is the 3 days, the AlphaGo Zero defeats AlphaGo 100-0. So also interestingly is that it's run on a single machine with 4 TPUs, compared to, I think it's like 8 GPUs and 40 CPUs or something like that, that runs the AlphaGo algorithm. The authors of the paper then scale up AlphaGo Zero from 20 blocks to 40 blocks. And this plot in their blog post that's linked in the description of this video shows the plot of how it improves its ELO through this self-play and this kind of a training loop over time in this AlphaGo Zero algorithm. The authors scale up AlphaGo Zero to a larger network from 20 to 40 residual blocks and have 40 days of training time amounting to 29 million games of self-play, and then they have 3.1 million mini batches of these 2048 positions, this ST, pi sub t, and then ZT, used to update the policy and value network. These are the results of AlphaGo Zero. So the scaled up AlphaGo Zero won 89-11 versus AlphaGo Master. So you frequently hear this reporting on the AlphaGo Zero that it's 100-0 versus the previous AlphaGo paper, and that is correct, but it's not 100-0 completely on this idea of having no prior human knowledge. So the AlphaGo Master is the same idea of AlphaGo Zero, which is described in their paper as well, different versions of AlphaGo Fan, AlphaGo Lee, AlphaGo Master, and AlphaGo Zero. But basically, AlphaGo Master still uses the supervised learning of the KGS to initialize the network, and more details that you can read about in the paper. I wanted to relate this idea of self-play training with the Monte Carlo tree search, as well as knowledge distillation. It's kind of interesting how you have the Monte Carlo tree search's distribution of the policy, and then you try to distill this into the original policy network, which I think is really similar to the knowledge distillation pipeline, where you have these large capacity models distilling information into the student lower capacity model by emulating some kind of a label distribution. So it's definitely an interesting kind of trend and connection across different disciplines of AI research. Thanks for watching this explanation of AlphaGo Zero. Some of the big takeaways from AlphaGo Zero compared to AlphaGo is the use of less prior information. You don't start off with the supervised learning of the human expert data, and the input state representation is just these history stacks of the board representations compared to these handcrafted features. It's also really interesting to see the policy and the value networks combined into this one residual neural network. So it's got more complexity in the neural network, and it's performing both tasks in one architecture. AlphaGo Zero is also really interesting for the way that they use the Monte Carlo tree search in the self-play loop in order to improve upon and train this neural network. I hope all this was clear in the video. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.